Okay, in this video I'm going to talk about the first Fermat-Torricelli point of a triangle. So let's say that we have an arbitrary triangle, and what we do is we construct the like equilateral triangles at the sides to the outside of the original triangle. So like this. So this is like equilateral triangle. Like this. This is equilateral triangle. And like this. So yeah, so and now we consider the intersection, we consider the lines connecting the vertices of the original triangle. So these 3 points with the vertices of this equilateral triangle, right? So this line, and this line. And there is a theorem that says that these 3 lines intersect at a single point, and this point is called the first Fermat-Torricelli point of this triangle. So let's denote the vertices A, B, C. So let's denote this as P, Q, R, and the theorem that says that the points, that the lines AP, BQ, and CR intersect at a single point. Yeah, so yeah, let's put it in brackets, which is called the first Fermat-Torricelli point of the triangle ABC. Okay, so let's prove this. So what we will do is we consider the intersection of two of these lines. So we have this triangle. We consider this equilateral triangle. This equilateral triangle. Well, it's not really equilateral. And this equilateral triangle. And so what we do is we draw 2 of these lines. So this was denoted P, and this denoted R. This is Q, and this is A, B, C. So we consider 2 of these lines, and the third one we don't draw yet. So we consider the intersection points of these 2 lines, denoted by F. So let's... So this is F, and so F is the intersection point of these two lines. So basically we need to prove now that that F belongs on the line like on the third line from B to Q. Like we need to prove that F belongs to the line BQ. If we prove that, then this would mean that all three lines intersect at a single point, right? So okay, so observe now that since these are equilateral triangles, so like they have like all angles are equal to 60 degrees, right? And then also we have that so okay, so so this is 60 degrees. And this is 60 degrees. Basically all these angles are equal to 60 degrees, right? So this angle, this angle, this angle, this angle, this angle, this angle, and this angle. But what we need now is that so consider the triangle ABP. You can consider so the triangle, and we consider what happens to this triangle when we rotate it clockwise by 60 degrees. So rotation about the point B. So we consider the rotation about the point B by 60 degrees, right? So with this rotation, so we notice that the segment AB, it maps to the segment RB, right? So basically B stays in place. B is not going anywhere in this rotation. So the point A goes to the point R, right? So like we rotate basically by 60 degrees around B like this. So A goes to R, and here also. So and P, the point P goes to the point C, right? And so the whole segment like AB, the whole segment AB maps to the segment RB. So when we rotate one side of an equilateral triangle around its vertex, like this side is mapped to another side, right? So the same way BP is mapped to BC. So in total, this triangle that I highlighted in blue, so the triangle ABP is mapped to the triangle RBC, right? So let me highlight it in green. So the blue triangle is mapped to the green triangle. Right. So this means, in particular, that that the angle. So like this angle in particular is equal to this angle, because these are the corresponding angles of this triangle that are mapped to each other under the rotation. So like when triangle is mapped under a rotation to another triangle, these two triangles are equal to each other. So therefore they have the corresponding angles must be equal to each other. So these two angles are equal to each other, and these two angles are equal to each other for the same reason. So now we consider the quadrilateral. So we draw this segment and we consider the quadrilateral ARBF. So let me highlight it in yellow. So this quadrilateral. So in the quadrilateral ARBF, we see that these two angles, like that I denoted as equal, so the angle FRB is equal to the angle FAB, right? So this angle is equal to this angle. So because they're equal to each other by one of the criterion of a cyclic quadrilateral, it implies that this quadrilateral ARBF is cyclic. Let me put point F more clearly because it's not visible, almost not visible. Yeah. So this yellow quadrilateral that I highlighted with yellow, it's cyclic, which means that all these 4 points lie on the same circle. So similarly, the other quadrilateral that I will also highlight it with yellow. This quadrilateral is also cyclic because the other 2 angles that I showed, so the angles FCB is equal to the angle FPB. So this implies that this quadrilateral FBPC is cyclic. So now, if both of them are cyclic, so one of the criterion of a cyclic quadrilateral is that the sum of the opposite angles is equal to 180 degrees. So because this angle is 60 degrees, so the opposite angle, so basically this angle, must be 180 minus 60 it would be 120, right? So the angle AFB is calculated as 180 degrees. Well, let's write full. So the AFB plus the angle ARB is equal to 180 degrees, but ARB is equal to 60 degrees because it's an angle in the equilateral triangle. So therefore the angle AFB is equal to 120. 180 minus 60. So this is 120, and similarly we have this angle calculated as 180 minus this angle in the other yellow quadrilateral. So the second yellow quadrilateral is also cyclic, therefore the angle BFC plus the angle BC is equal to 180 degrees. This is 60 degrees. Therefore, the angle BFC is equal to 120 degrees. So, yeah, so this angle is 120 degrees and this angle is 120 degrees. So it implies that the third angle, like this angle, is also 120 degrees, right? Because like we calculated as 360, the full angle, minus this two. So we calculate the angle AFC as 360 degrees minus the angle AFB minus the angle C, or let's write it BFC. So this one is 120, this one is 120, so 360 minus 120 minus 120, it would be also 120. Now we consider the third yellow quadrilateral, this one, and we see that the sum of the opposite angles in this quadrilateral is 180. So the angle AFC plus the angle AQC is equal to what? So AFC we just calculated this is 120 and AQC it's simply 60 because it's an angle in an equilateral triangle. So plus 60 degrees is equal to 180. So when the sum of the opposite angles is 180, it means that the quadrilateral is cyclic. So this third yellow quadrilateral is cyclic, is also cyclic. AFCQ. So the quadrilateral AFCQ is cyclic. So because it is cyclic, when we so now I will draw this segment, but notice that we don't know that like if BF and FQ are on the same line. So it like, let me deliberately draw it that it would not look like on the same line. So let me draw it like this, something like this. Yeah, so it's kind of not, we don't yet know if they are on the same line. So we draw this segment, and because this quadrilateral, this third yellow quadrilateral is cyclic, we conclude that this angle is also 60 degrees because it's equal to this angle, right? Because these two are inscribed angle subtending the arc AQ in this circumcircle of this quadrilateral, right? So so because it is cyclic, it implies that the angle AFQ, is equal to the angle ACQ, and ACQ is simply 60 degrees because it's an angle in the equilateral triangle. So AFQ is 60 degrees. So now we see that AFQ is 60 degrees and AFB is 120 degrees, right? So the angle QFB, so the angle QFB is calculated, so the QFB it's this angle. This angle, right? So it's calculated as the sum of this angle and this angle. So one of them is 60, another is 120, so the sum would be 180. So QFB is calculated as the angle Q, or let me put it this way, AFQ plus the angle AFB, right? So QFB is calculated as QFA or AFQ, the same thing, plus AFB. So AFQ, we just calculated it, it's 60 degrees. And the second angle AFB, we calculated it somewhere. Yeah, it's here. AFB is 120. So 60 plus 120, it's equal to 180. And when the angle QFB, when the angle is equal to 180, it means simply that the point F belongs on the line QB. And this is exactly what we needed to prove. So we need to prove that F belongs on BQ. Well, I wrote here QB, it's the same thing. The same line, doesn't matter. So yeah, so this is basically what we need to prove. So so F belongs on BQ. It means that BQ passes through the intersection point of the other two lines, and it means that all three lines intersect at a single point, which is the Fermat-Torricelli, the first Fermat-Torricelli point of this triangle. So this concludes. Oh, let me write it. So this implies that so AP, BQ, and CR intersect at a single point, and this concludes the proof.